Our next speaker is Matilde Lalin. She will talk about non-vanishing for cubic L functions.
Okay, well, thank you. Thank you for the opportunity to speak, and also thank you all for coming to my talk. This is joint work with Chantal David from Concordia University and Alexandra Floria from Columbia University. The object of this project has to do with moments of Dirichlet L functions. So in this talk, we'll be concerned with, by moments, we mean the sum. In principle, we mean the sum over the characters mod D with D, the conductor, bounded by certain parameter that over number field will be X, but for most of the talk, we'll be talking about function fields. So we are going to go to modify this a bit. And we're going to do the sum over the primitive characters. So the star is indicates that we are summing over primitive characters. And what we are looking at is the L function evaluated at the central value, 1/2 to the power of K. And our motivation for looking at this has to do with non-vanishing results. And so this idea of non-vanishing goes back to a conjecture by Choula, who conjectured that L in 1/2 chi is different from 0. In principle was for quadratic characters, but then this is believed to be true more in general. Now, how this relates to non-vanishing, like, is due to actually the Cauchy-Schwarz inequality. So if you take the, say, the first moment, and you apply Cauchy-Schwarz to it, and basically, so in each term of the sum, you imagine that you have the L value times 1, but you only have the terms where the value is different from 0. So when you do that, oh, something happened to the screen sharing. Sorry about that. It's like the there. Okay, should be there now. Okay, I'm gonna keep it not on presentation mode so that just in case. Okay, so basically, Cauchy-Schwarz allows you to bound the first moment by the second moment times, well, the square root of the second moment times the square root of the number of characters for which the L function is different from 0. So when you flip things, you get a lower bound for the number of characters for which the L function is non-zero by the square of the first moment divided by the second moment. Now, what do we know in terms of the moment for quadratic Dirichlet functions? Well, there is a conjecture coming from random matrix theory that the K moment should be given by asymptotically by constant times X times log of X to the power of K times K plus 1 over 2. And actually for the first 3 cases, this is known. And for K equals 4, this is known conditionally under GRH. Now, if you apply this, what happens is when, say, you apply Cauchy-Schwarz, like the one I showed you, when K equals 1, K equals 2, what happens is that there is the powers of log are unmatched in a sense. So your lower bound for non-vanishing gives you X over log of X. And well, okay, so this is good in a sense. Okay, goes to infinity, but if you think about it, the number of characters is of size X. So what this is giving you is that the proportion of non-vanishing characters goes to 0. So it's not an ideal result. I mean, you want results that say that, well, you want to prove that they are all non-zero, but if not, you want results that say that there is a positive proportion of characters for which this is non-zero. And so just computing the moments doesn't work. Now, Soundarasham found a way of working with modified moments, and I talk about modified moments later, but the point is that he got non-vanishing for a positive proportion of 7/8. Now, for cubic characters, you can try to do the same gymnastic, and in this case, there is some subtlety here because you could consider basically the third roots of unity are not in Q. So either you consider Q and the third roots of unity are not in Q, or you add the third root of unity, and then, well, you have to think about Heckel functions. But basically, you can ask this question. And so what is known in this case is the case K equals 1. So for K equals 1, for Q, the result is known due to Bayer and Yang, and it gives what we would expect. And then for the Kummer case, the case where Q adjoins the third root of unity, then actually the only result that is known is result of Luo for a thin family. So it's a family where he takes a square-free conductor, and that's actually not the case. You don't always have square-free conductor. So the size of the whole family will be x log x, but Luo's result is x because he doesn't take the whole thing. So this is all that is known for cubic characters over number fields. Now we'll be leaving the number field setting and talk about the function field setting. So basically, we're going to replace Q by FQ adjoint T. And the thing that is important here to keep in mind to follow the tongue will be that our X, so the size that we have, will be replaced by the norm of something, will be Q to something. So when we have X before, now we'll have Q to something. And we have also the formula for the Riemann zeta function gives you an idea of how the digit L function is replaced. So you go over the sum of the F monic polynomials, and you take the norm of F, and the norm of F is Q to the degree of F. And an important distinction in this setting of function fields is that now we know that the Riemann hypothesis is true. And so with that, many things come in for free, and so some conditional results stop being conditional. So for quadratic L functions over function fields, there is a conjecture that is pretty much analogous to the one over number fields. So basically here, X is replaced by Q to the 2G plus 1, and the log of X is now 2G plus 1, is the exponent. And so what is this 2G plus 1? So basically, we can think of these characters associated to, say, an extension. And this extension will be given by, say, a very concrete model. If you want, y squared equals a polynomial. And this G will be the genus of the curve determined by this model. So we have to go over either 2G plus 1 or 2G plus 2. Depending on the model we choose. So like if we want to be concrete, we fix one of them. So for this case also, it is known for K equals 1, 2, 3, and 4. And also there is a non-vanishing result, although in this case it's due to other techniques. So it's due to one-level density techniques by View and Floria. And also something surprising is that there is also some vanishing result by Wanlin Li. She proved, well, different cases, but at least Q to the 2G plus 1 over 3 vanishing. So still this doesn't contradict the kind of result we are after, okay? Because this vanishing is much smaller than the total number of characters, but still is interesting what it says about Choula's conjecture in this case. Now what we want to talk about is the qubit case for function fields. And so the first result we have has to do with the first moment. And we recover the first moment in both the non-Kummer and Kummer cases. So non-Kummer is when we take the base field FQ to be Q congruent to 2 mod 3, so the third root of unity are not present there. And then the Kummer case is when Q congruent to 1 mod 3. And this result is really the first of its kind in this direction, because like I said before, over number fields, the only thing that is known is for a restricted set. So this is a result for the whole set. And gives you x log x if you want. You can think in those terms. And then for the non-Kummer, it gives you x. Now, for the rest of the talk, I'm going to just talk about the non-Kummer case. So for the non-Kummer case, with this first moment and some bounds for the second moment, the immediate result that one gets is this non-vanishing of Q to the G over G. So this is kind of the same that we had before, x over log x. So it's good, but maybe not so so good. Then there's another result by another paper by Ellenberg, Lee, and Schusterman, where they actually improve this to Q to the G over square root of G. And let me say just that the one level density that Florian used for quadratic doesn't really give a positive proportion in the cubic case. And what I wanted to present today mainly is the result that we actually got positive proportion. So for the non-Kummer case, we have that the number of cubic character, primitive cubic characters with genus G, that that the L function doesn't vanish, is greater or equal than some fixed constant, some explicit positive constant times Q to the G. And now the general strategy for proving this result is, like I kind of hinted before, it has to do with using modified moments. And so this is an idea that goes back a long time ago to Selber, and then it is what, like I said, Soundararajan used to prove positive proportion for the quadratic case in the number field. And basically, the rough idea has to do with introducing a function on these characters that morally behaves like the inverse of L1/2 chi. So I wrote there a formula that at this point doesn't make a lot of sense, but basically the L function, the derivative function, the characters will be like chi over the square root of S. And what I'm going to do is to have the inverse, I'm going to multiply by the Liouville function. So that gives you the inverse, okay? Obviously, it's not the inverse, and you don't want to inverse 0, okay? But morally, this is what it gives you. And so when you do, and then what you do is you compute this modify first moment and second moment. So for the first moment, because, well, the first moment already was some constant times Q to the G. So it will still be some constant times Q to the G, but maybe different one. And then for the second moment is very hard to compute. So we don't know how to compute it, but we bound it. And before, the typical bound would be like log x, okay? So G, Q to the G. But because we are multiplying by 1 over L in each term, we get like a bunch of ones. And so it's like morally we are counting the number of characters for which this is different from 0. And so we managed to get Q to the G. So this is kind of the very vague idea of what we are doing. And so when we apply Cauchy-Schwarz, we get a positive proportion. Now, there are two parts of this. So one has to do with computing the first moment, and the other has to do with computing the second moment. So for the first moment, I don't want to talk a lot about this because it has to do with the previous project. Just let me say that it's not very different from just computing the regular first moment. The ingredients that we use have to do with the approximate functional equation that gives you some principal and some dual term. The principal term is a sum of things. So when you take the part that has to do with sums of cubes, you get the main term. by using Perron formula. And then for the non-cubes, you kill them using Lindelof, which is true here. And then the part that is the hardest and more involved has to do with bounded the dual term. And the dual term comes from a generating series of cubic Gauss sums. And we do more than bounded. We actually do some estimates that allow us to get some cancellation. And so we get more than just bound. I mean, we get a better error term. That's for the first moment. And for the second moment, the idea is, like I said, our idea is to get a bound, but it's a good bound. Instead of GQ to the G, the idea is to bound just get Q to a G with an explicit constant. And we use ideas of sound for that for almost sharp bounds for moments of the zeta function. Harper, who did sharp bounds for moments of the zeta function, and Lester and Radziwill, who did sharp bounds of mollified moments in the family of quadratic twists of modular forms. So the first ingredient has to do with the bound for log of L by a short Dirichlet polynomial. And basically what we have is that we have an infinite sum and we bound it by a finite sum, but we pay a price for that, okay? So the finite sum is sort of bounding the degree of these, the polynomials that we are going over. But obviously, the smaller the bound, the bigger the price you pay. You have a term G over N. So basically, you want G over N to be small. So what we do is we do this G over N to be constant, but a very small constant. So at the end of the day, we're going to take N to be G over the exponential of 90, to give you an idea. And so this is a bound for the log of L, but what we want to compute is the bound for L, really. And so you have to take exponential. So when you take exponential, it looks like you lose again, because again, your finite sum becomes an infinite sum again. But then there is this idea by Lester and Radziwill where they bound exponential with a finite sum under certain circumstances. Okay, this is super fast. I only have 3 minutes. Okay, so in sum, you have a bound for the log, you take the exponential, and then you bound the exponential by a finite sum on top of that. Now, if you look at what you get when you apply this sum, so there is some combinatorics that you can apply, and this suggests you what you should take as a mollifier. So all I'm going to say is that, okay, so once you look at what you get with this bound, you get the mollifier. And the mollifier is what I mentioned, it has to do with the chi divided by the square root of f, the Liouville function. And then there is some extra function, nu of f, a multiplicative function, and that is coming from the combinatorics of considering what you get when you take powers of p. Now, another thing that one has to be careful about has to do with the interval. So if you remember, we were bounding things up to n, and n was like a multiple of g. A very small multiple of g, but still a multiple of g. Now, if you do that, it doesn't really work because we want to get q to the g as a bound, but if you take a multiple of g, you get some extra logs. Okay, so we want to get rid of the logs. And so what you have to do is you have to split the interval in small intervals, and it's a union of actually intervals that they shrink in size. So the bigger G is, the more intervals you take. And this is an idea due to Lester and Radziwill. And so there is some subtlety there. And then you have to work over each integral, so interval. So actually the mollified moment, you have to look in each piece. So here I give you like inequality in one of the cases to give you an idea how things work. So basically what you apply Cauchy-Schwarz, and it's kind of fun because you replace, it's like you have your mollified moment, and you add a factor in each term that is actually bigger than 1, bigger or equal than 1. And then you use that to apply Cauchy-Schwarz. So it looks like you're making things worse, but actually you're making things better in a way. So you end up with the second moment again, with the bound that we know, like q to the g times g. But then the other term is kind of bigger. It kind of wins over the power of g. So basically, you are kind of using one term to win over the bad estimate on the other. So it's actually very cute. And so just wanted to finish with what is the result now with the explicit constant. Okay, so if I take the proportion, what you get is that non-zero for at least 0.47 times e to the minus e to the 182. So this is a positive number, but if you ask a computer, the computer will tell you that this number is zero. Okay, it's very, very, very small. And but this is coming from the method, so there is basically we will need to have something very radical, like a radical new idea to have a a substantially more positive proportion. So with that, I finish my talk. Thank you very much for your attention.
Thank you.